Hello, my name is Corbin Kowalt. I'm the co-chair in the Department of Physics here at Case Western Reserve University, and it's my privilege and honor to welcome you to today's event. I just want to tell you a little bit of what today's event is and why we're here. First of all, this is the weekly Department Physics Colloquium. It's also Physics 166 for those of you who are graduate students. This is our optional mandatory course for graduate students participating in the colloquium. But in particular, this is the colloquium where we celebrate the Michelson postdoctoral prize lecture, which will be given by Ben Lemon, who will be introduced a little bit later. We're also here to celebrate the source of the prize. The prize is named after Albert Michelson, the famous Michelson and Morley experiment, which was done here at Case Western on the campus of what was the Case Institute of Technology. Professor Albert Michelson worked with another faculty member from the Western Reserve University to conduct an experiment that demonstrated that the speed of light was independent of any assumption of an underlying medium or ether. And the experiment was the first experiment in modern physics that paved the way for Albert Einstein's theories of special relativity in 1905 and the world that came after that. So we're here to celebrate that as well. And we're also here to celebrate and acknowledge the accomplishments of young scientists from Northeastern Ohio who are finalists in the International Science and Engineering Fair, which we'll hear a little bit more about now. So rather than talk about why we're here, I'm going to have others come forward and explain what we're doing and how it works and to celebrate further. So let me introduce Glenn Starkman, the co-chair in physics, who will talk more about science in Cleveland.
So as you noted, since we're in a physics department in Cleveland, we are contractually obligated to start with the Michelson-Morley experiment, which occurred in a basement a short walk from here, where Albert Michelson and Edward Morley used an exquisitely sensitive interferometer to try and fail to detect the Earth's motion through the luminiferous ether. Their famous null result helps set the stage for Einstein's special relativity and remains one of the cleanest examples of how a careful negative result can reshape the foundations of physics. The Michelson postdoctoral prize lectureship is a legacy of the centennial of the Michelson-Morley experiment, a grand festival bringing together science and the arts to celebrate this transformative experiment. The prize was conceived by the physics department about 30 years ago to celebrate young physicists from anywhere in the world who are doing outstanding research and may also have a talent for explaining it. In a few minutes, my colleague Kurt Hinterblicker, I'm doing really well with this, Kurt Hinterbickler will tell you about this year's laureate. Cleveland has long been a launching pad for young people who started here and went on to scientific excellence. Donald Glaser, who developed the bubble chamber and opened new windows on the subatomic world, studied physics and mathematics at what is now Case Western Reserve. Polycarp Kusch, whose precision measurements of the electron's magnetic moment were crucial for quantum electrodynamics, earned his undergraduate degree in physics here. Ralph Gardner Chavez, chemist and educator, is best known for his research on plutonium during the Manhattan Project. After earning his PhD in chemistry at Case Western Reserve University, he later became a professor at Cleveland State University. And Terry Sejnowski, a Brain Prize winner and pioneer of computational neuroscience and neural networks, built on a foundation in physics and mathematics that began in this environment. On the invention and technology side, you see the same pattern. Herbert Dow's work as a student on the chemistry of brines helped launch what became Dow Chemical. Charles Brush's training in Cleveland fed into practical arc lighting and electrical systems that literally changed how cities were illuminated. Garrett Morgan invented the gas mask and three-way traffic light. More recently, Larry Hornbeck trained in physics here and invented the digital micromirror device, the core of DLP projection technology that underlies many projectors and digital cinemas we now take for granted. But science in Cleveland is bigger than any one campus. It includes world-class biomedical research, not just here, but at the Cleveland Clinic and university hospitals, the VA and Metro, NASA Glenn Research Center, where people work on propulsion, materials, and aerospace technologies that connect Cleveland directly to the space program, It includes the Cleveland Museum of Natural History, Holden Arboretum, and the Metro Park Zoo, where research in public education in ecology, evolution, climate, and conservation are part of the region's scientific fabric. So when we welcome the winners of the Northeast Ohio Science and Engineering Festival into this room, we are not just introducing you to one department, we're inviting you into a dense ecosystem. From historic experiments in relativity to Nobel Prize-winning work in medicine, physics, chemistry, to inventions that powered industry and digital displays, to cutting-edge research in neuroscience, ecology, and space science, you are sitting in the same kind of environment that helped shape Glaser, Kush, Sejnowski, Dow, Rush, Hornbeck, when they were closer to your age than ours. The projects you are doing now may feel small, but so did theirs at the time. Science in Cleveland has always depended on curious young people who are willing to measure carefully, think critically, and follow the evidence where it leads. And today you are part of that story. And to help celebrate those people, I want to introduce Don Schiappini, who is a Cleveland native whose interest in science goes back to his days inventing an electric-powered go-kart to ride around his Cleveland Heights neighborhood, and later winning the 1960 Northeast Ohio Science and Engineering Fair. Higher education, including a PhD in experimental particle physics, took Don away for a while, but he eventually came back to his hometown where he taught at Notre Dame College and became an entrepreneur, first in the software industry, but most recently innovating in solar panel systems to power our future. Don tells me that he is on a mission to see how many different federal agencies and organizations he can work with before he runs out of ideas. Don is an expert at tapping into the strong public, private, and educational cooperation that can be found here in Northeastern Ohio, and he gives back to that collaborative atmosphere. Over the years, he has mentored hundreds of future innovators by hiring students and graduates from Cleveland area colleges. He has never lost his enthusiasm for learning and tries his best to attend our weekly elementary particle and astrophysics lectures here at Case Western Reserve Physics Department. Please join me in welcoming Don Schiappini.
Thank you, Glenn. So today we're celebrating this new concept of science in Cleveland. And this wouldn't be happening without the support of Juan Loy-Paul, who is the president of the Northeastern Ohio Software and Engineering Fair, and the muscle of Glenn, which you all know about. So to begin with, to be blunt, this science in Cleveland it's an advocacy opportunity, a bit of PR, so we can promote what we do and help the community better understand what we do, how we do it, and why it's important. So Science in Cleveland, this is the first Science in Cleveland event. It's going to be anchored by two signature events, the Michelson Morley Postdoctoral Lectureship and the Northeast Ohio Software and Engineering Fair. I love Michelson Morley. To me, it's the most important experiment that's ever been done. And I know some may disagree with that, and I'll be happy to discuss that with you outside behind Rockefeller at 5:30. Michelson was all about a mysterious substance that permeates the universe. It's very fitting that today Ben is going to give us a lecture about some other mysterious stuff that permeates the universe. Ben, congratulations on being this year's Michelson Morley postdoctoral lectureship winner. NEOSEF is the other anchor of this of science in Cleveland, and NEOSEF has been putting on the regional science fair since the 1950s, and it collaborates with the International Science and Engineering Fair, and we take the best science projects in the local science fair and we send them to compete in the International Science Fair. So to our ISEF finalists, congratulations. And you're going to find that going to ISEF for a week is going to be a life-changing experience. But we should all not be satisfied until our science students can actually letter in STEM. Letter in STEM. You know, like in football? In 1960, I was a ISEF finalist, as Glenn mentioned. But 1960 was also the first time I stepped into the Rockefeller building. It's one of my most memorable experiences, sitting downstairs in Beryl Robbins' office at his desk while he painted very highly radioactive cesium-137 on some aluminum foils for my science experiment. I can't imagine the paperwork that we'd have to go through to do that today. So, well, finally, we're actually seeing some real world results of our advocacy because the county executive, Chris Ronayne, has issued proclamations to all our Science in Cleveland celebrants. And we have those today to pass out to Ben and the science fair finalists. Unfortunately, there may be some miscommunication because only one of our science finalists was able to show up. But we have 9 of them. We'll make sure they get it all, and we'll find out what happened to the communications. I mean, I propped the door open. So let's pass this out now.
So this is a proclamation from the county office, county executive, Chris Ronayne, celebrating the achievements of Ben Lehman on being awarded the 2025 Michelson Morley Postdoctoral Prize Lectureship. And says, now therefore be resolved that the county executive, Cuyahoga County, Ohio, does hereby honor and recognize Ben Lehman, PhD 2025, Michelson Morley Postdoctoral Prize Lectureship winner, and his talk on testing the particle dark matter paradigm and extends sincere appreciation on behalf of Cuyahoga County.
So we have 9 proclamations for the students. I think a few of them are here. But we're going to read all of these, at least what they did and the name of their research. So, Aishman Day. Come on down. Aishman Day is from Solon Schools, and his research is decoding GLP-1, digital twins to separate neural pathways from metabolic pathways in brain health. Congratulations. Bradley Field. Bradley Field's from Chagrin Falls High School, and his winning project is machine learning for coral bleaching diagnosis and forecasting using images and environmental data. Bradley, congratulations.
For Shanhao Wu, now therefore be resolved, the county executive of Cuyahoga County hereby honors and recognizes Shanhao Wu from Solon Schools on his winning project, motorized arm rehabilitation device for disease and sports-induced movement impairment.
Okay, we'll make sure he gets that. This is for Ayat Jafar, Hawkins School. Optimizing electron transport in organic solar cells using self-assembled monolasers, a molecular approach to zinc oxide surface engineering. So,
And to Yifat Wang from Solon Schools on her winning project, Impact of Mechanical Design on Piezoelectric Energy Collection.
She's not here, Sarah.
Nandita Srikumar from Solon High School on her winning project. Okay, here we go. Epigalacticin 3 gallate, a natural therapeutic agent in Alzheimer's disease targeting CDK5 and CRMP2 pathway. Congratulations.
Aran Bal from University School for his winning project, Early Stage Inference of Wildfire Spread Dynamics Using Physics-Constrained Deep Learning.
All right, Hassan Al-Shafi from Normandy High School for his winning project, Beyond the Riemann Hypothesis, a novel geometric approach to deterministic prime location for enhanced cryptography security.
And Camille Valchi from Solon Schools. For his winning project, Analysis of Gene Expression and ADAR Editing in Fluoroquinolone-Treated Astrocytes Exposed to Cadmium.
So we have two more proclamations, one for Case, Corbin, and one for the Northeast Ohio Science and Engineering Fair. One. He's making more stuff.
So this is from the county executive to celebrate the legacy and contributions and continued success of the Northeastern Ohio Science and Engineering Fair.
Iowa County, Ohio, does hereby honor the Michelson Morley Postdoctoral Lecturer at Case Western Reserve University, celebrating its commitment to excellence in science in recognition of outstanding young researchers and its role in sustaining the region's proud legacy as a center of discovery and innovation. Yeah.
Yeah, okay. It's probably after all.
Yes, we send.
Good question. Great. Right, and it's my pleasure to call my colleague Fred Hitlerbeck to introduce our Michelson Morley postdoctoral prize. Thanks.
Okay, so it's my pleasure to introduce Ben Lehman, this year's winner of our Michelson Postdoctoral Prize lectureship. So Ben is a theoretical physicist, but also has close ties and interests to experimental physics, and his area of expertise is all things dark matter. So we're going to hear today all about dark matter, what we know, what we don't know, what we might hope to learn in the years to come. So Ben is a product of the Bay Area. He grew up in the Bay Area. He did his undergrad degree at Stanford University. He did his PhD at UC Santa Cruz. And now he holds the Pappalardo postdoc at MIT, which is one of, if not the most prestigious postdoc posts in the country for this field. So before we start, I have the award certificate for the Michelson Prize. And I have the award check itself. Yeah. And without further ado, take it away.
Thank you, Kurt. I have had such a wonderful time over the last 2 days getting to know so many of you in the department, getting to chat with many of you both in and outside my field of expertise. And as Dawn remarked, it's so appropriate that I get to talk about dark matter, and in particular, testing the particle dark matter paradigm in recognition in honor of Michelson and Morley. And I want to just acknowledge that what I'm going to tell you about today is not going to resolve once and for all whether dark matter is a particle or not. You'll have to wait a little bit longer for that. But I would like to just point out that everything that we are doing in dark matter science is about understanding the effects that we are seeing, whether this turns out to be all a set of null results or not. If Michelson and Morley have taught us nothing else, it's that a null result can be tremendously important. So I want to start here in space. We now have an excellent description of the universe at a wide variety of scales. You've probably seen pictures like this where each of these dots is not a star, but actually an entire galaxy. And what's remarkable about the era we live in now is that we don't only know how to describe these galaxies, we know how to describe what we are not seeing. If we could see the actual matter, if we could see the actual density in the universe, we would see a picture that looks more like this. This is a computer simulation. But to break it down for you, in the universe, the energy density, only about 5% of it is atoms, molecules, you, me, everything we can see. Most of it is actually dark energy, which is driving cosmic expansion. I'm not going to say another word about it in this talk, but you should feel free to ask me about it later. And about 30% of it is dark matter. So what is dark matter? Dark matter is this additional component of the energy of the universe that behaves like matter in many ways. As the universe expands, it dilutes just like it was dust. It clumps together, but it's invisible. It passes through us. Everything that we know about dark matter tells us it should be here in the room with us right now, and yet we don't notice it. So how do we actually know about this component? Where does it come from? Well, there are actually several ways that we have come to understand that dark matter is out there. And I want to start with the most important historical context, which comes from galaxies. Some of the first evidence for the presence of dark matter came from galaxies and galaxy clusters. Actually, the very first observation was in the 1930s of this galaxy cluster called the Coma cluster, where a fellow by the name of Fritz Zwicky observed that the velocities of the galaxies in the cluster were too fast for that cluster to stay together. If this was a cluster in equilibrium, if it was just moving around, orbiting, then there must be additional matter, additional gravity holding all of those galaxies in place. Now, later on, the same effect was actually observed on stars in galaxies. If you just measure how fast are stars moving as you go out from the center of a galaxy, which is what this plot is showing you, you'll see that the velocities stay high as you go further out. That's not what you would expect if most of the matter, if most of the gravity is coming from the center of the galaxy. You would expect it to dip as you go back out. We've also seen it in more dramatic contexts. This is a picture of what we call a bullet cluster. This is actually an example of two clusters, two galaxy clusters, that passed through each other. And we can measure the presence of the gas. That's what's shown in red. It's hot, it radiates. And we can also measure the total gravity by looking at the bending of light. And that's the blue. So you can see here, the gas isn't where the gravity is. What happened here is that two clusters collided, passed through one another. The gas is sticky. The gas stuck together in the middle. But all of the dark matter that was following those galaxies, those dark matter clumps moved through one another. And that's why we see those blue edges. So these are some of the classic examples that people talk about when just introducing what is dark matter. But I actually want to go a little bit further than that, because there is more than that that really convinces us that dark matter is something out there. So one thing we can do, actually, to see the presence of dark matter is actually observe the bending of light by individual clumps of dark matter. So here, this is a picture of a radio observation where there is a background galaxy that we see multiple times because the light is being bent by the mass in the foreground. And we have many examples of this now where we can actually measure how the light is bending around a dark matter clump. We can also go to even larger scales, larger than galaxy clusters. So the best evidence for dark matter, if you ask me, really comes from cosmology. If you measure the clustering of galaxies, they actually follow the pattern in the background because galaxies form inside these dark matter clumps. Each one of those yellow nodes in the picture, that is a dense dark matter cloud that would host a galaxy. And so you can make a statistical prediction out of that. You can say, what are the distance scales where I expect pairs of galaxies to appear relative to one another? And you can match the theory perfectly. This plot was actually made by a member of this department. You can also look at the distribution of galaxies at even larger scales than that. You can look for a phenomenon we call baryon acoustic oscillations, where ordinary matter, because again it's sticky, in the early universe, when everything is together in a big thermal soup, the ordinary matter has sound waves in it. And those sound waves make little perturbations in the matter density that today we can see as a scale in the separation of galaxies. So that peak you see in that plot, that is actually telling you about the sound waves in the very early universe. And the fact that we can assemble galaxies on those scales is entirely thanks to the dark matter that isn't colliding. Now we can also look at the cosmic microwave background. These are the very largest scales we can see. And here we have a remarkable agreement between theory and data. This does not work without dark matter or some other component. So we have many independent lines of evidence that all call for the same amount of extra energy, extra gravity. Now, we actually have assembled this into a beautiful picture of how structure forms in the universe, how we end up with the universe that we see. We start off with some initial perturbations in the density of the universe at very, very early times. These might come, for example, from theories of inflation. And then, at some point, we end up with a separate pair of fluids. One is all the ordinary matter, and it's coupled tightly to all the photons, all the light. It's a single fluid of light and matter, and that is behaving separately from all of the dark matter, which isn't colliding at all. It's just hanging out and just clumping together under gravity. The ordinary matter eventually separates from the light. The light that separates is what is known to us today as the cosmic microwave background. And the baryons, the particles of matter, they end up settling into the clumps or halos that are formed by that collisionless dark matter. And they are what give us today galaxies and other gaseous structures that we can actually go and see. So we have this beautiful, highly predictive theory, which requires just a couple of ingredients for this additional component of the universe. But of course, I do want to introduce another possibility. You might say, everything that I have introduced so far about dark matter is strictly gravitational. All of the evidence that I've pointed to only involves the gravitational interaction. So what if we just don't understand gravity very well? Gravity is actually notoriously complicated. It's one of the forces we understand the least well. And so you could imagine that maybe all of these effects are just due to modifications to the laws of gravity. Well, this is actually a very rich question, and there has been a very active program of research, including by people here at Case, to understand whether that could be the case. And there are some very tantalizing hints that, in fact, the universe is as you might expect from a modified theory of gravity. So this is, for example, a plot of how the masses of galaxies relate to the velocities of the stars in the galaxies as a function of those galaxy masses. And the sort of simplistic dark matter prediction is actually the dashed line. And the modified gravity prediction is the dotted line. So from pictures like this, it seems like modified gravity might have some things going for it. The story turns out to be much, much more complicated than that. There are good reasons why most people in the field believe that the additional energy, that is additional gravity, is really because of another matter component of the universe and not a modification to gravity. I'm going to say, if you are curious about those reasons, you should feel absolutely free to ask me at the end of the talk. For right now, I want to confine ourselves to looking at particle dark matter on its own terms and just assess how should we understand this additional energy in the universe if it is matter. Now, if you're going to try to understand some additional matter that is invisible, that is ghostly, that doesn't scatter with anything, this can't be an ordinary particle of the kind that we know. It has to be beyond the standard model of particle physics. So early on in the history of dark matter, people started to ask, could dark matter actually be related to problems that we already know about in the standard model? So there are a few problems. For example, there's the hierarchy problem, the fact essentially that the Higgs mass is so small. This is a problem that could be solved by additional particles that would enter through a mechanism called supersymmetry. That could explain dark matter. We don't know how neutrinos get their masses, and any effort to give them masses often gives you additional particles that could account for dark matter. There's also what we call the strong CP problem, which is most naturally resolved by an additional particle called the axion, which could be the dark matter. So there are lots of problems in the standard model that seem to be crying out for a new particle that behaves exactly like dark matter, that's invisible, that's ghostly. And we have many lines of evidence that suggest that we have exactly this kind of particle in our universe. Now there is one class of particle that I want to just give special mention to. And to introduce what this kind of particle is, I want to just set up for you, where does dark matter come from? Any successful theory of dark matter should explain why we have dark matter in the universe today. Why is it here? One of the easiest ways to get dark matter in the early universe is to just produce it from ordinary matter. If dark matter and standard model particles, that's SM, if they talk to each other, then they can annihilate into each other. So you could imagine that at some very early time, they were in equilibrium with each other. This plot is showing as a function of time how the abundance of these particles behaves. So if at early times, ordinary matter and dark matter were scattering together very often, they were in equilibrium with each other, then the amount of dark matter would be kept basically the same as the amount of ordinary matter. But if at some point in the history of the universe, as the universe cools and expands, if dark matter particles can't find each other to annihilate and make standard model particles, you're going to have this decoupling, where the amount of the dark matter in red is going to stop depleting. And that is going to leave us with the amount of dark matter that we have in the universe today. The remarkable thing is that if you assume that the kind of interaction between dark matter and the standard model is what you would expect from a new particle at the weak scale, exactly where you need it to fix these problems in the standard model, you turn out to get about the right amount of dark matter. That's a big hint, right? This suggests that maybe there is a new particle at the weak scale that already accounts for the problems of the standard model and gives us dark matter. We call such particles weakly interacting massive particles, or WIMPs for short. Now, how could we go about looking for WIMPs, and how have we? There are basically three ways. One way is to make it. Right? So let's just have this cartoon here of particles going into other particles, so time goes from left to right. So you could imagine taking standard model particles, crashing them together, and seeing if you can annihilate them to make dark matter particles, just like happened in the early universe, if this is right. You could break it. You could do the opposite process. Look for dark matter particles annihilating into ordinary matter particles. Or you could shake it. You could look for scattering, where you exchange energy between standard model particles and dark matter particles, but you don't annihilate them. And these correspond to capabilities that we actually have. We can make dark matter in principle at colliders. We can look for indirect detection signatures, that is, signatures of annihilation coming from the dark matter around us in our own galaxy. And we can perform laboratory tests with direct detection, where we look for dark matter particles to scatter with a detector and impart some energy. Now, the really important thing here is that the amount of dark matter is not independent of the size of those interactions. If I need to get the right amount of dark matter, that tells me what the coupling strength has to be in the annihilation process. That's usually related to all the other processes of interest. So that same coupling is going to show up in each of these kinds of experiments. That means that for a given WIMP-like dark matter target, I usually know exactly where to look with one of these experiments. So we know how to look for WIMPs. Can we find them? Well, we have spent a long time trying. So this was a paper from a little while ago, and it pointed to an upcoming moment of truth for WIMPs as dark matter. And it argued that if we don't discover them in the next 5 to 10 years, we would witness their inevitable decline as a dark matter candidate. This was 2010. No WIMPs yet. And now we're used to seeing titles that look more like this. So, has the WIMP begun to wane? Well, arguably, we haven't seen the full promise of the LHC immediately discovering all of these super partners and immediately giving us a new zoo of particle physics. But in thinking about where to go from here, I actually want to take a step back to say the WIMP is not dead. There is plenty of interesting parameter space left for WIMPs to be dark matter, even though we've built lots of experiments, even though we've done lots of searches. This is a hard business. And we actually know exactly what's going to come down the pike over the next couple of decades. These three mechanisms that I just introduced, we are still using them at a variety of experiments that are still running. And in each of these cases, we can't rule out all of the WIMPs in the next 20 years or so. There are still very interesting scenarios that we are going to probe. Most of the attention now is on future and far future facilities, new kinds of experiments that are going to allow us to probe the rest of the WIMP scenario. So that's going to happen. That is part of the program. But I think it's worth taking a step back at this point, away from the WIMP for a moment, to just say, what do we actually know about dark matter so far? We actually know a lot. We've learned a lot over the last 40 years while we have been searching intently for WIMPs as dark matter. We know, for example, that dark matter is cold. And by that I mean we know the velocity distribution of the dark matter particles. We know they are non-relativistic. We know how fast they are. I can tell you how fast they are in this room if they're here with us. We know it is dark. We know it doesn't scatter with light. We know it doesn't scatter very strongly with itself. We know it behaves like matter. That's actually an incredibly important constraint. In the cosmological context, as the universe expands, the amount of dark matter dilutes as you would expect for dust, not, for example, like radiation. We know that it clusters. It forms a huge variety of structures on a wide variety of scales that make very, very non-trivial predictions for how the universe looks across different scales. They hold up beautifully. We know that dark matter is stable. We have very stringent bounds on how much dark matter can decay over cosmic history. It's a very small fraction. And finally, we know that it is what I'm going to call essential, by which I mean we wouldn't be here without it. In our universe, galaxies don't form without dark matter. The universe is expanding too quickly. The gas is too collisional. You need this extra gravity from dark matter to bring it together. So the fact that we are here is a testament to dark matter, or potentially some other energy density in the universe, that is allowing galaxies to form. So I like to say that when people talk about the need to discover dark matter, I think that's actually not the right terminology. I would say we've actually already discovered dark matter. We have a very clear picture of this stuff being there. So what don't we know about it? What is the actual nature of the dark matter problem now? Well, I would argue that in the past, the logic was you would understand the particle physics of dark matter. So for the particle physicists in the room, you would know the Lagrangian of dark matter. You'd find that by doing collider experiments. Then you would work out all of this other phenomenology. You'd know, is it many particles instead of one? Does it go through phase transitions? Does it interact? Does it have many components? All of these things you would learn from the microphysical structure. Now, however, we should probably think about turning this around. Most of the stuff that we have learned about dark matter particle physics actually comes from the emergent large-scale behavior and not the other way around. So we need to look for broad, systematic probes that are fairly model independent, that give us some sense of how dark matter behaves, even if we don't yet learn exactly what it is. Now, fortunately, we actually have a lot of ways of doing this that are fresh. Because while we've been searching for WIMPs, a lot of new tools have come on the market that are enabling new kinds of tests of dark matter particle physics. So I'll give you just a few examples. Quantum sensors. These are new technologies that are enabling new kinds of laboratory searches with dramatically higher sensitivity. Cosmology is advancing. We have new kinds of observations that are giving us new kinds of sensitivity on dark matter's interactions. We have gravitational waves. This is an entirely new tool. It's like a new way of seeing the universe, a new kind of light. So we're able to rapidly extend our searches. We're able to use upcoming instruments to go to all kinds of different scales that we've never been able to probe before. And we're able to probe what are arguably the most pessimistic scenarios even using gravitational waves. So let's think about some generic questions about dark matter. Starting with this, is dark matter actually made of particles? Well, I like to think about dark matter in this plane, where the x-axis is the mass, and the y-axis is how strongly it interacts with us. So the lowest possible interaction strength is gravity. Everything interacts via gravity. You'll notice that the mass spans this enormous range. There's actually 90 orders of magnitude here between the lower bound and the upper bound. It's bounded, we know that much, but it's a wide range. There are actually three sort of sectors of this plot. If dark matter is very light, the particles actually have long wavelengths, and they overlap. And dark matter starts to behave more like a classical wave or field than like particles. On the other hand, if dark matter is extremely heavy, it could be in the form of compact objects, like black holes or some other kind of granular stuff. It could clump together in very, very tight bundles. In the middle is really the billiard ball regime, where dark matter is just a bunch of diffuse particles like a gas. So what I really want to get at is what are the kinds of phenomenology that we might expect from these different classes of particles? How could we then go and test these possibilities? And I actually would argue that with the tools that I just showed, we actually have ways of probing all of these scenarios that I just listed. So we have this exciting opportunity now with these new tools, stepping away from the WIMP for a moment, to say, what are the different kinds of behaviors dark matter can have? How can we diagnose those behaviors in a short time scale? And our goal here is not necessarily to say what is the mass of the dark matter particle. The goal is to have some new qualitative statement about how dark matter behaves, to add to that list of things we know about dark matter. So that is the philosophy with which I'm going to show you a few examples of doing exactly this. First, I'm going to show you how we can use laboratory experiments to test whether dark matter actually came from a thermal soup in the early universe. Next, I'm going to show you how we can test whether dark matter has internal interactions, whether it talks to itself. And finally, I'll say some words about whether the dark matter could be super heavy or tightly clumped together. So let's start with this production question. Did dark matter come from a thermal soup? And here, I want to turn to these laboratory experiments. We've gotten very good now at making experiments that can search for dark matter scattering in a detector. If it's coming through the lab, every now and then it hits an atom, and you can see it. Well, we've gotten good at that for WIMPs. We've gotten good at that for heavy dark matter particles. As it turns out, we are allowed to have dark matter particles of fermion statistics, at least, all the way down to the keV scale, which is a little bit further than we've been able to probe, by about 6 orders of magnitude, actually. We also have some particle-like territory in light bosons. So the program of the next few years in laboratory detection is to be able to explore this light dark matter regime, where we haven't been able to search for WIMPs. And there is a definite target here that comes from production. If dark matter came from the early universe out of that thermal soup, we know there is a line to hit on this plot of dark matter mass and cross-section where we should expect to find it. Now, the problem with going to this light dark matter frontier is that it's actually quite a bit different physically from searching for ordinary WIMP-like scattering. If you have weak scale dark matter that's hundreds of GeV in mass, that's going to behave like a billiard ball in your detector. It's just going to smash through, hit an atom. But if you're talking about really light dark matter, where the energy scales of these processes are even smaller than the scales binding together the atoms in the material, now you're sensitive to the entire wave function of the detector. And so quantum effects become important, material effects become important, everything changes. So the strategy that we've been using over the last few years has been to switch to detecting light dark matter using what are called collective excitations, or if you like, quasi-particles. So let me explain what that means. Ordinarily, if I think about a dark matter experiment, I think about dark matter interacting with ordinary elementary particles, like an electron, right? But those aren't the only kinds of excitations that I can have. I can also start with excitations that involve multiple particles, like these. Right? So these are examples of normal modes that constitute excitations that you could quantize. You could make new kinds of, effectively, particles out of these multi-particle excitations. And rather than just interacting with one electron at a time, dark matter can interact with these effective quasi-particle excitations. So, here's the deal. By cleverly designing a detector, we can actually engineer a system where we can adjust the behavior of those quasi-particles. We can make a system that has the excitations that we want, that basically has the artificial particles that we want, that dark matter can see and scatter with. That means that we can directly adjust the sensitivity of experiments to dark matter if we can figure out how to adjust these quasi-particles. That's exactly what I've been busy with over the last several years. So we now have this beautiful theory picture that I've helped put together where we understand the role the quasi-particles play in the language of response functions. Basically, we have a way of describing how the dark matter interacts with one particle at a time, and we have a totally different way of understanding how the material or the system as a whole responds to that added energy and momentum. In this case, for ordinary electronic scattering, if I scatter dark matter with electrons, it turns out that the response is actually related to the dielectric function. So if you've taken an E&M class and you've seen a dielectric constant, it's the same object that controls how dark matter scatters in a condensed matter system. Now, what that means is that we can use the levers that we already understand for dielectric functions, dielectric response, which are very, very well understood. Generations of condensed matter physicists have worked on this. We can use that to design new and better detectors. So we actually have done this. We have a set of superconducting detectors now. They look like this. They are little tiny wires, superconducting wires. And when the dark matter comes through, it has a very strong rate of scattering with that superconducting system. It makes these excitations called Bogoliubov quasiparticles in the superconductor. And we can actually see those quasiparticles inside these superconductors. We actually use this to make an experiment that we call Crocodile. It's the Quantum Resolution Optimized Cryogenic Observatory for Dark Matter Incident at Low Energies. That took a lot. And it is actually the most sensitive experiment in the world for light-dark matter. It looks like this. And we are actually able to set world-leading bounds just by having one exposure of our tiny prototype device for just about 400 hours. I can actually show you what this looks like. Here, this plot is showing you the constraints as a function of the dark matter mass. So lower is better on this plot. That means lower cross sections. And about the bottom of the plot is where we need to get to in order to be able to probe the expected cross sections from cosmological production. If we can get there, we can make a statement about whether dark matter is produced from that thermal soup. Now, we're making quick progress. So the blue curve, that's where we were in 2021. The green curve is where we are now. We've got a lot of experimental capabilities now to actually put these ideas from condensed matter physics into practice to build these really amazing detectors. So in the next generation, we actually already have prototypes that are showing off some of these capabilities. We should be able to get pretty close to the bottom of this plot. So it's really a matter of 5 to 10 years before we can actually test this idea concretely. Now, with that help from condensed matter physics, I now want to turn away from materials entirely. Material science, quantum sensors, that's one of the new tools we have at our disposal. Another tool that we have is cosmological observation. And so I want to say a word about what we can get for dark matter's interactions from cosmological observations. So one thing we can do here, the simplest thing we can do, is just look for observables in cosmology that are sensitive to the exchange of energy between dark matter and us. There are plenty of these. For example, the amount of hydrogen versus helium in the universe. That depends on whether energy is leaking between dark matter and the Standard Model. We can actually set constraints on dark matter interactions. Here, higher is better. We can actually set constraints from various observations of the amount of atoms in the universe, the cosmic microwave background. We can bound how much energy has flowed between dark matter and the Standard Model. But this is still only thinking about interactions between dark matter and us. If we want to get more generic and really say something meaningful about the structure of dark matter physics, we should think about internal interactions. What do I mean by that? Well, I talked about 3 different kinds of interactions, right? There's the direct detection processes, where the dark matter is exchanging energy with us, but not annihilating. There's indirect detection, where it annihilates and makes things we can see. There's production, where we make it from standard model particles. But I have neglected to include this leg. What if dark matter is interacting with itself, scattering with itself? I just want to put that into context. Why is this important? Well, think about the standard model. Think about us. Think about our particles. If I take, for example, an electron, it has a remarkably complicated set of interactions because it sees all the other particles in the standard model. If I just compute the interaction rate between an electron and a positron as a function of energy, it has spikes. It's not smooth. There are resonances in it as it sees the masses of other particles. That leads to a complicated cosmological history. The amount of particle species that are in the plasma at any given time is changing over time. There's sound waves. There's all kinds of dynamics that depend on this complicated particle physics. So does the dark sector, if there are multiple dark matter species, or if there's communication between different dark matter particles, you could get a similarly complicated cosmological history. Now, as it turns out, we can actually diagnose that. So I like to say that structure reveals structure. We have theory structure, the ideas that we have about how dark matter particles might interact with one another. And then we have literal structure. We have the clumps of matter that dark matter forms. And if we can observe those small clumps, they tell us about the theory structure of dark matter. Why is that? Well, if I look at small galaxies around me, which means I'm looking at the small dark matter clumps, I'm actually able to tell different things about what that dark matter clump distribution is like. And that depends on the physics of the early universe, of the interactions between dark matter. So for example, this here is a picture of 3 different scenarios where the dark matter is a little bit warmer in each picture. So as I go from right to left, I start off with a very cold dark matter. It clumps very easily because there's not a lot of velocity pushing it out of those potential wells. You can see it's really granular, a lot of small scale structure. As you move to the left, now the dark matter is getting a little warmer. It's getting faster, and you wipe out that smaller structure. So that means you'd be missing galaxies. You can actually quantify this statistically in an object we call the matter power spectrum. Basically, this is as a function of length scale, how much overdensity is there in the universe? How much structure is there? And what you can actually do is use this to directly see interactions between dark matter particles. So let me show you an example here. Let's say that I have a dark sector that doesn't talk with us at all. It's entirely secluded. It only interacts with us via gravity. But I'm going to say there are 2 kinds of particles. There is dark matter and some radiation, just like we have radiation around us from the cosmic microwave background. So if the dark matter and the dark radiation can exchange energy, there are lots of things that could happen. I'm going to just consider the simplest thing that could possibly happen. The simplest example of a deviation from a nice smooth interaction rate. What if these 2 species are originally coupled together? They're scattering very often. As the universe expands, they stop finding each other, they stop exchanging energy, and then for a moment they come back into equilibrium with each other because that interaction rate goes up. Could we see that? Could we see it if the interaction rate looks like this? This is a cartoon. The answer is absolutely yes. If you have this kind of a bump in the interaction rate, you are actually going to see that effect in the matter power spectrum, in that statistical description of the clumping of matter. That's what the right panel is showing you. So as you go to higher and higher bump sizes, you get more and more bumpy suppression of structure on small scales. So here we can actually interpret this quantitatively. We can separate out the effects of the amplitude of the bump, the time that it spends in equilibrium, when that actually takes place in the history of the universe. And that actually allows us to study different possible theory structures. So for example, it might be that there are resonances in dark matter interactions, just like there are in the standard model. That would do this. It might be that there are what we call Sommerfeld enhancements, which can give lots of spiky behavior in the cross sections. There might be phase transitions, just like there are in the standard model, that could also change interaction rates suddenly. And in each of these cases, we can actually study the matter-power spectrum with the next generation of cosmological surveys and understand, did these events take place? Are those features of the dark matter theory landscape? So, we are now able to tie those next generation measurements directly to dark particle physics, which is going to give us an important handle for studying what kind of particle physics dark matter exhibits. And I want to finish with one more possibility, one more direction to chase, which is that dark matter might be clumpy. What do I mean by clumpy? Well, clumpy is a broad word. I really mean that most of the dark matter mass is found in some very small areas. The simplest way to think about this is actually to relate it to another favorite object of the theory community, and that's black holes. It is possible that dark matter is made entirely of microscopic black holes. Microscopic meaning about the size of a hydrogen atom. Now, this is actually one of the very first ideas for the nature of dark matter. To my knowledge, it may actually be the first proposal for dark matter. There are papers from the 60s talking about non-luminous matter. Maybe it's these newfangled black holes that the theorists discovered. But they're actually very attractive as a dark matter candidate. They don't need much. If you have a way of producing them, and there are ways to do that, then they behave exactly like a cold dark matter candidate. They're also a good proxy for studying this kind of clumpy or clustered dark matter in general. Anything that is really, really clumpy, that forms very, very dense objects, is going to look in some limits like black holes. So this is sort of the poster child for clumpy, compact dark matter. And with that said, we've actually done a really good job over the last 30 years of testing this. So this plot shows the constraints that we now have on black holes as dark matter. This line here at the top, that represents 100% of the dark matter. So where the constraints fall below that line, it means that you can't have all the dark matter in black holes at that mass. You'll notice there's a gap. This is what we call the asteroid mass range, even though it's not really asteroid mass. You could have all of the dark matter as asteroid mass black holes. Now, I said before, hydrogen atom size. I meant physical size. I meant radius. As it turns out, black holes are really dense. If you have a black hole with the radius of a hydrogen atom, it has the mass of a very large asteroid. This is really hard to test. We've been trying for at least 5 years to really aggressively close this gap, to really see, is dark matter possibly made of black holes? And now I can tell you about one of my favorite ways that we might do this, using the solar system as a particle detector. Solar system, as it turns out, is a very, very sensitive instrument. It's gigantic, has a large area, so even if these black holes only come through very rarely, we have a way to see them. So let me actually show you how this works. You can actually estimate this using ordinary Newtonian mechanics. If I have a small black hole that passes by, let's say, Mars, with some impact parameter, that's b, it's going to get some it's going to impart some velocity difference to Mars. You can compute that just by doing this integral. And now you can ask, if Mars is now drifting with this new imparted velocity, how long does it have to drift before I can actually tell, given my precision on Mars's position, that there has been this kind of perturbation to its orbit? You can do the algebra. It turns out that you expect about one detectable event every 26 years or so if dark matter is made of asteroid mass black holes. Why is this so exciting to me? It's because we've been measuring the distance to Mars with extreme precision, around 10 centimeters, for the last 30 years. So we actually have, right now, on disk, we have data that could contain evidence of a black hole passing through the solar system. Now, of course, you shouldn't rely on this back-of-the-envelope napkin estimate. You should do something more proper. So indeed, I can show you simulations where black holes pass through the solar system, they don't have to get particularly close to any planet to still impart a velocity big enough for us to see. If you actually compute the amount of distance that planets gain away from us, given their perturbation by a black hole, the plots look like this. The back of the envelope is the dotted line, so it's got the right idea, right order of magnitude. But if you really want to look for these perturbations, you need the full template. You need to understand exactly how the planets move in response to one of these objects transiting through. That's a big job, but we can do it. So the solar system is actually going to be able to probe at least part of this asteroid mass range. And I want to say, by the way, if you like press attention, write about black holes in the solar system because the press loves that. So there are a number of newspapers that covered this work. There were a lot of interest from people who just worry about being hit by a black hole on Earth. I've gotten that question more times than I can count. My favorite press attention, though, is definitely this PBS Spacetime episode. The reason it's my favorite is I found out about it when my dad texted me saying, "Oh, there's this really interesting thing. You should check it out. It might be related to what you do." Turns out it was. Okay, one last thing. We can also search for these tiny asteroid mass black holes using a method called femtolensing. This is brand new work. This is work in progress. In femtolensing, light comes in as plane waves, and the black hole acts as a tiny lens. Because that lens is so small, physically, it's actually smaller than the wavelength of visible light, you end up with diffraction patterns. So those diffraction patterns have peaks and troughs of intensity, right? And those peaks and troughs have different spacing for different colors or different frequencies of light. What this means is that if you look at the spectrum of the light that you see at any one point, you are going to see that you're at the peak for red, you're at the trough for blue, you're at the peak for green, etc. So as you pass by, if your unlensed ordinary light from a source looks like this flat line, if you pass through the path of a lens, you're going to see this wiggle in the spectrum. And that is the hint to you that a tiny black hole is there. What I find so exciting about this is that on my laptop at the moment, I have 700 gigabytes of data from the NICER telescope, which is an X-ray telescope, and it has actually produced this shaded green limit as a real limit from actual data that is already probing some of that asteroid mass range, already ruling out some parameter space for black holes as a dark matter candidate. And there is room in the future for that purple line. That's an X-ray experiment that we're going to have in about 10 years that should be able to probe most of this space. The tiny bit at the edge there are other methods that'll cover that. So we will know, within about 10 years, we will know whether dark matter is made of black holes or not. I want to speak just for a moment about the future possibilities. There are a lot of different directions to take, and I've only mentioned a few, focusing on those things that are sort of immediate, where we can immediately get some understanding of how dark matter behaves. But these are not the only tools we have at our disposal. So for example, next generation experiments, those things I called out at the very beginning, they're going to happen, and if they do, the next generation of experiments will be sensitive to a very wide variety of dark matter phenomenology. So in particular, the next generation collider experiment, in particular in combination with new indirect detection, new kinds of observatories for looking for dark matter annihilation, they will be able to test, is dark matter a WIMP or not, period. There will be no wiggle room at that point. Now, we also have these lovely new laboratories in black holes. Since we have gravitational waves to observe merging black holes, there's all kinds of new science that we can do just using gravity. You can actually look for new interactions between black holes mediated by new particles or by new environments. And you can actually see those effects by changes in the gravitational wave spectrum that we observe from those black holes. This is a totally nascent field. We don't know yet what all the opportunities are, but we do know that there is a tremendous opportunity to use gravity alone to probe a lot of dark matter physics. I'm going to wrap up here. What I want to leave you with is that although dark matter is complicated. Although there are lots of different possibilities for what dark matter could be, you don't have to just think about searching for dark matter as doing a million tests, eliminating a million candidates. What we want to do is continue the program that has actually been very successful for us so far. We have learned a tremendous amount about dark matter by doing broad model-independent tests that are sensitive to these kinds of broad properties of dark matter. And I am very confident that in the next few decades, we're going to gain new pieces to add to that list of items we know about dark matter, thanks to these new tools we have at our disposal. So if you ever hear someone say that dark matter is at a dead end, I want you to tell them that is absolutely not true. Not only is there tremendous opportunity in dark matter science, but we actually have a number of decisive, informative tests that are upon us now. And I will stop there.
So we have time for a few questions. Any students first? Yeah.
The conventional parts, you mentioned you 400 hours to introduce a DOM. So field directions, please could you comment on dissipation is kind of that long, and it's probably going to take longer for considering the directional requirements. And more comment on the directional requirements, how long do you think it will?
Yeah, good. This is really a question that is going beyond what I said in the talk, because one of the really important capabilities of a dark matter detector, if you want to actually believe that you have found dark matter when you see a signal, is to be able to establish what direction the dark matter is coming from. Now, why is that important? Because we know what direction it should come from. We are orbiting the center of our galaxy. The dark matter is distributed roughly homogeneously in our galaxy. So just like if you're driving a car and you roll down the window, there's a wind facing the opposite of your direction of motion. Exactly the same thing happens here with dark matter. So if you have an experiment that can tell what direction the dark matter particles are coming from, you can say, yes, I know the dark matter particles are coming from that specific direction on the sky, which means I have indeed discovered dark matter and not something else. So what do you need in order for that to work? Generally speaking, depending on how anisotropic, how directionally sensitive your detector is, you need realistically tens to hundreds of events in order to establish that you're seeing a directional signal. So in principle, if we saw a large rate and we wanted to do a directional search, then we would want to run it for at least as long a time to get those hundreds of events. We only saw 15 events, which is not enough to do a directional search meaningfully. It's also not parameter space where we expect dark matter to live, because this is a prototype scale experiment. But does that answer the question? Great.
How do we know how fast dark matter should be moving relative to the galaxy?
Yeah, so we actually have a number of ways of determining this. The easiest way to do this is basically to use the virial theorem. Right? So if a system is at equilibrium, there's a relationship between the potential energy and the kinetic energy of any particle in that system. So you can use that to set a relationship between the velocity of stars in a galaxy and the velocity of dark matter particles. Then you can actually go and do something more sophisticated. You can do detailed simulations, computer simulations of galaxy formation. And once you do those simulations, you then see not only can you resolve the velocity distribution of the dark matter in great, full glory, it agrees with the naive estimate where it should, and it also has really interesting implications for what kinds of galaxies form. So there's a whole literature, a whole field of understanding based on these kinds of dynamical questions. What kinds of galaxies do we expect? How do we match that data?
I was wondering about negative results. And what I see here is, from the beginning of the lecture, a real conviction from various sources of evidence that dark matter does exist. And then in the second half, I'm seeing we have some ways of detecting it. Do you feel that those three methods you outlined are exhaust the field?
Good.
If they're all negative, do you start looking for other ways? Do you start looking for other structures that dark matter protect?
Excellent. So this is something I think about a lot because I like to sleep well at night, and I don't sleep well at night if I don't have a program that tells me what to do if everything comes out null. And indeed, there are ways that are sort of guaranteed wins, where you know you will learn something definitively. Now, the way to do this is to use gravity alone, which is hard. It is doable, but it is hard. So I'll give you one example of this. We know that massive black holes, or intermediate mass black holes, so sort of hundreds to thousands of solar masses, they typically form in environments where you would expect them to have a lot of dark matter around them. And there has been a very robust effort now to simulate what does that dark matter do as those black holes come together. Does it change how the gravitational waves come out of those black hole mergers? And the answer is, yeah, it seems to. So in principle, in the future, when we have the appropriate gravitational wave instruments, we should be able to measure the presence of dark matter around those black holes on a very, very small scale. The details of dark matter interactions might also be contained in that information, right? But that's the kind of measurement where you see something, right? You see direct evidence for the small scale behavior of dark matter in a regime where you couldn't try to accommodate it, for example, with a modification to laws of gravity. So that's one example, but there are many others where you use gravity to try to understand the detailed small scale structure.
Okay, if there's no more questions, let's thank Ben again.